Hi everyone, thanks for joining. So today we are hosting Jiafei on the talk regarding towards robotic foundation models that can reason. So he's a PhD student in computer science and engineering at the University of Washington, advised by Professors Dieter Fox and Ranjay Krishna. His research focused on foundation models for robotics with an emphasis on developing scalable data collections and generation methods, grounding language models in robotic reasoning, and advancing robust generalization in robot learning. His work has been featured in MIT Technology Review, GreekWare, VentureBeat, and BusinessWare, and his research has been published in top AI and robotic venues, including ICLR, ICML, and all. And he has earned a lot of awards such as Best Paper at Ubiquitous Robots 2023 and a Spotlight at ICLR 2024. He's a recipient of both ASTR National Science PhD Scholarship and undergraduate scholarship. So, yep. Welcome, Jiafei,
Thank
to
you.
our multimodal group. Yeah.
Thank you.
Yeah.
Let me share my screen.
Yep.
Are you able to actually see my screen?
Yes.
Am I inside the screen sharing mode?
Yeah.
Okay.
We are able to see it. Yeah. Thank
Okay.
you.
I'll just begin. So thank you for inviting me to the Cohere multimodal talk section. As the host mentioned, my name is Jiafei. I'm a third year, also graduating final year PhD student at the University of Washington. And today I'll be sharing a bit on some of the work that I have been working on throughout the entirety of my PhD, and focus on the notion of towards robotics foundation models that can reason. And I think my vision, or at least, I guess many people's vision of robots, is to be able to do tasks in an everyday home, having in this case, a humanoid to bring us a bottle of wine, wipe out our countertop, store our keys, and even doing those mundane tasks in this very unstructured environment. That's the goal that we all have. But sadly, to break everyone's hopes and dreams, everything that the robot has done in this video are purely teleoperated. It means that someone is controlling the robot behind the scene. And so what do we actually need in order to achieve that North Star that I just described, and hopefully having an autonomous robot that's able to do all the tasks that were shown in this video? I think we need a generalist robot model that can understand instructions and act in an unstructured environment. And if you look at how we are going to get there, we need to first look at the past in terms of what people have been doing. So in the traditional form of robot autonomy, there is a lot of these customized robots that has been around for decades in factories, and there is always a human expert that does that programming, and you have a specific or specialized agent that's able to perform a downstream task in a very structured environment. But I think moving forward to today's context, to achieve the goal or the vision of the North Star that I just showed, we need to have a new form of robot autonomy, whereby we need to leverage on general purpose robots to actually learn to perform general purpose behavior. And the way to achieve that maybe comes from a generalist robotic model. And in the early days of the deep learning era, robot learning policies has mainly focused on this specialized model. And this specialized model often comes in this kind of structure when you have a visual encoder that encodes the observation. You have a language encoder that tries to take in some kind of language instructions and also encoding the robot state with a robot encoder. And you train together jointly to train action decoder that tries to predict action. And some of these prominent examples could be like action chunking transformer, diffusion policy, and etc. And this is good because you are able to get this specialized model that's trained for very specific single or multitask on a small data set domain. But that is not good enough, in the sense where we want to have this general purpose behavior that transits across different embodiment, across different tasks. So now with the advancement of language model and vision language model, we have been seeing more of this generalist model, paradigm, in which now you are adding another layer in between the encoders and the decoder, which is the language model or some form of vision language backbone. And that's good because now you are able to have work of this kind of generalist robotic models, for example, from Gemini Robotics, from Google, or like Groot M1, Physical Intelligence Pi0, and MolmoAct from AI2, which I'll talk about later. And the trade-off is that for such generalist model, we have to train them at large scale internet scale equivalent robot data. And by But since people are already doing so, we are able to achieve at least some resemblance of this generalist robotic model, and which is good. But the question I would like to sort of counter ask is that, is that enough to actually just learn action alone? For example, just now in the scenario where I mentioned about, placing the keys on the valet tray, how do the robot actually learn this kind of spatial reasoning of what is on to, versus in between or above or to the left or to the right? And even going a bit further to look at, is some of these generalist robotic model able to have this concept of episodic reasoning, which in the way that, the robot is the one that sort of stores the wine earlier, and now he has to learn to sort of retrieve from where he actually store. So does it have this concept of memory? And even going further beyond to argue that, we need some form of semantic reasoning whereby, we want to have the robot to be able to detect, if he has dropped anything from the grocery bag that he's trying to help us to carry. And if he does, to be able to, understand that failure that occur and be able to come up with recovery strategies to adapt to that change. And after all, we are trying to let this robot operate in an unstructured and an open world. So can we sort of achieve that by purely scaling data? I think it's really tough because, generalist robotic model are really data hungry. So if you look at the largest data set in robotics, which is OpenX embodiment, and if you try to, tokenize it on the same vocabulary scale, you get approximately 100 million tokens. And if you look at that in comparison to like Common Core C4, which is trained early days of GPT, that's 1.4 trillion tokens. And that's a scale of 14,000. So the idea is that you are not able to sort of scale robot data in the same level as other domains. And in fact, if you try to scale, it'll probably take you about 100 years to reach Quen 2.5 level for robotics data. And, it just won't scale. And furthermore, even in the scenario that you are able to sort of scale, not the robotics data, but other data that's necessary for training VLMs or LMs specifically for robotics tasks, we realize that, with the existing data set that's being used to train right now, it's just not enough. So one example would be for spatial reasoning, to try to ground using VLM is inaccurate for manipulation, even if you add some kind of prompting. So for example, tasks where you want, the VLM to sort of, ground the concept of, pouring tea into the mug. So where is the place that you want to pour into? What do you define as into? So even with GPT Quen, or even with Pivot, which is like a prompting method from Google, you're not able to get a precise spatial location. And furthermore, how do you translate that spatial representation into actual physical actions that the robot can take? So that is still a question mark to many of us. And looking at the episodic example, even in language model, it's really easy for us to sort of add previous context or conversation into context. But for robotics, such observations and actions are just computationally intractable to be incorporated. And also because many of these approach today leverages behavior cloning, which is Markovian in nature. So a simple task as, trying to store and retrieve a client, most of these end-to-end policies are not able to do it because that requires memory, and many of these policies are memoryless. And furthermore, if you look at the frontier models, are they able to even look at a video sequence as simple as the robot trying to pour a cup of milk and detect that the robot has already failed in doing this and provide even further explanation on why it fails? So Gemini 1.5 is not able to do that. So I think there is still a huge gap. But the good thing is that we are learning lessons from how people are training language models and vision language model that, when data is not able to scale further, we want to sort of empower it through reasoning. And this concept of reasoning means that you still keep the input and the output the same, but having some form of intermediate steps or representations or tokens that sort of generates more information from the same amount of data that was used. And we see a huge success of that in like language model training with like chain of thought prompting, self-consistency, to like, multimodal examples of like set of mark, and even going as far as like, seeing that a lot of these reasoning models are able to achieve state-of-the-art performance in this kind of AGI benchmarks. And lastly, we want to be able to sort of learn to ground natural language into spatial affordance. So we show that with our method that's empowered by reasoning, which is RoboPoint, we are able to take in that instruction and now generate 2D coordinate points that annotates where that insight represents. And furthermore, with MolmoAct, which is our action reasoning model that leverage reasoning in space, we are able to actually bridge the gap from the spatial representation going all the way into learning the actual action that's required to perform the task. And for the episodic example, with our SEM2X, we are able to train a memory-centric, transformer-based robot policy that's able to learn from demonstrations and not just memorize the demonstration example, but really make informed decision based on its past observation that it remembers. In this case, we are able to solve that task I just described. And also, moving one step forward, we are also able to demonstrate with AHA that, which is a failure reasoning vision language model that we train to be able to detect failures that occurs in image, and then sort of provide the necessary reasoning context of why it failed. And showing that we are able to go beyond, just the training distribution and generalize across different embodiment, different tasks, and different robot form. So today I'd like to present some of my work in the context of these three parts, which covers the spatial reasoning, episodic reasoning, and semantic reasoning to help us build a better robotics foundation model that can reason. And I'll talk a bit about the future direction. So for the first part, spatial reasoning, I'll talk about the work RoboPoint, which is a vision language model for spatial affordance prediction in robotics. So I think spatial representation matters a lot for robotics foundation model. And oftentimes, there's a lot of ungrounded actions which lead to a weak tie to the observation and poor generalization. So for example, if you use pi 0 and you give an instruction to put the green tin can in between the plate, this is what pi 0 will try to do. It's trained on a huge amount of demonstrations. We even fine-tune it further. And you can see that it actually struggles to identify what does it mean to be in between. And I think right now you will just drop it on one of the places. And what RoboPoint is trying to propose is that RoboPoint learns to point in the point of generating 2D coordinates on the image plane for spatial affordance prediction. And why do we use pointing? Because pointing is the most intuitive mechanism in which humans communicate our plans. And compared to language, pointing provides much more precise guidance to robot behavior. And with that, we train a RoboPoint that is instructionally tuned to point. And how it works is that you just feed in the observation of a robot, and then you give a natural language instructions, for example, place the orange at the bottom step, and RoboPoint will be able to generate a sequence of 2D coordinates. And using some of the robotic system that already exists, you are able to bridge the gap of moving the robot to the exact location on that 2D coordinate. And the way that we actually make it work is that we try to learn spatial reasoning from purely simulation data. So to train RoboPoint, we need to generate a bunch of spatial affordance prediction data. And the way we do it is that we use the scene synthesizer from NVIDIA. We generate hundreds and thousands of environments. And then we systematically create assets, placing them in these environments. And because you know that these are all simulation, you know the spatial relation between each object. So you can generate this kind of object reference. And then with that, you draw a bounding box on the object itself, using kind of the off-the-shelf bounding box detection, and then you create annotation point. And then the next thing you do is that you remove that object from the simulation and you re-render the whole scene. So now you will have this kind of free space affordance prediction points. And with that, we are able to do full instructional fine-tuning of Lava 1.5, and we basically freeze the encoder and the tokenizer and only train the projection and the language model to do alignment. And then with that, the model is able to take in natural language instructions of spatial reasoning and then output the necessary 2D coordinates that reflects that. And for real world, real world execution, we are able to use RoboPoint together with the depth from the depth camera and create the 3D points in order to move it using a motion primitive. And for some empirical result with RoboPoint, I think back then when we first started this project, there isn't this kind of evaluation of how good is pointing on 2D image. So we actually have to manually curate a data set called where to place, where you get humans to annotate natural language instruction and generate ground truth segmentation masks of where the point should fall given that natural language instruction. And we see that RoboPoint outperforms back then, the state-of-the-art models like GPT-4, even with in-context learning. And we also show that RoboPoint also still serves as a general purpose VLM by evaluating it across different benchmarks, VQA benchmarks, and show that it still maintains this capability. So with RoboPoint, we're able to explore interesting applications that shows the usefulness of the action representation. So for manipulation, the example I gave just now, followed by this one, which is to place the object into the left part inside the pizza box, which is really hard. But then roboticists have to design specific heuristics to figure out where this location is. And furthermore, as I mentioned, RoboPoint is a VLM that's sort of like a general purpose VLM. So we're able to prompt it in a way that, giving an image of a car, looking forward, how do we get to the carpool lane? And for those people who live in the US, you know that the carpool lane is always on the left of the leftmost lane. And then RoboPoint will be able to answer us and telling us to go to the left of the leftmost car. And then we can ask RoboPoint to generate that point. And yes, is prediction consistent? It's always going to generate the same prediction for the same given context, even if it's a video. And furthermore, you can also use it for navigation. So you can navigate not only reference to an object, but even to in terms of free space. And beyond that, we show that RoboPoint is a view-dependent and view-independent relation. So for example, if you want to ask RoboPoint, to locate the right side of the blue cup, no matter how you change the camera, the right side is always the same. And for independent, you can see that as you are moving, the center of the point will always retain the same condition on that language. So what has RoboPoint make an impact? I think when RoboPoint came out, we showed that pointing capability starts to develop in frontier models. Before RoboPoint, many of these other methods are not able to get good performance on 2D pointing tasks as seen by this benchmark point arena. But after RoboPoint and even MolmoAct's Pixmo dataset came out, suddenly all these frontier models are able to have that pointing capability. And furthermore, pointing is really intuitive for robotics. As a result, NVIDIA has already integrated that with their Jackson hardware. There's an online tutorial that actually helps people to get set up running RoboPoint on some of these edge compute device. But the question is, can such visual representation be used for manipulation beyond pick and place? So for example, if you want to pour me a cup of tea, if you use RoboPoint, I think RoboPoint will just be able to draw 2 points. But in order to actually solve the task, we need a plan to be able to steer a node-level policy. And furthermore, beyond a plan, we need to have some sense of depth to be able to reason over the action in a closed-loop manner. And if you try to do all this reasoning of its action just using language alone, it's not going to solve the task. If you feed ChatGPT with this image and tell it to do that same task, you'll generate a very detailed plan, depth estimation, even the predicted points. But none of this could actually work because this plan was never grounded into the scene. So what do we want? We want a single model that can sort of do it all. We want a robot brain that can generalize to new environment, new tasks, new behavior, and new objects. And with that, we introduced MolmoAct, which is AI2's flagship action reasoning model that can learn to reason in space. So how MolmoAct will try to solve this task is that MolmoAct will first perceive the scene and then generate perception token. And when you decode this perception token, you get observation in 2.5D. And then MolmoAct condition on that will generate a plan. And that plan will be known as a visual reasoning trace. And you decode that, you can actually visualize that plan on the 2D image plane. And then condition on all this, MolmoAct will try to predict, robot control in terms of action that the robot could take to actually achieve the task. And beyond that, MolmoAct is a completely open-sourced action reasoning model. We open source everything from the training code to the data, to even the post-training data, in fact. And you're able to show that MolmoAct is able to generalize to different tasks, different embodiment, and even different environment. So how do we build such action reasoning model? It all starts with a language model. So if you go from a language model to a visual language model, you're basically doing visual language alignment. And when you go from visual language model to visual language action model, you're training on action data. You're doing some form of visual language action alignment. I guess for action reasoning model, how do we achieve? We go from VLAs to ARM in a way, but we incorporated these intermediate reasoning steps through this action chain of thought that I'll mention later. But before that, we need to be able to even pre-train with enough data to have a base model that's good enough. And the way we sort of look at it is that we need to use open source robot data. But the problem is that open source robot data is really not of quality and quantity that's enough, for such training. So for example, if you look at the OpenX embodiment data, there's data that looks like this, which has really low quality visual observation. You have data that has like weird natural language instruction. You have robot data that's collected by Google that basically doesn't do anything for at least about 8 seconds. And if you convert it to like actual frames, there's over 100 frames of not doing any action. And in fact, for the droid data set, you have occasions where the robot is basically learning to grasp air. So the first thing to do when we try to devise MolmoAct is that we look at cleaning up the data. And after cleaning up all the 1 million trajectory, we sort of narrow down to 3 data sets that we thought was really useful, the RT1, the bridge, and the BCZ. And we further fine-tune them down to 190,000 robot trajectory. However, that's not enough. So we spent another month to actually collect MolmoAct data set, which is an in-house data set that's collected by us. We collected it for like many different household tasks with like strict requirements for our data operators. And we also show that, we are able to collect very well calibrated data. And we also collected, atomic skills that's also on tabletop, such as like, for example, pick up the plate and put it on the stand. Do non-prehensile tasks like, closing the drawer. And with that, we're able to collect much more high quality demonstration per task and having more repeatability in that task. So for people who are in robotics, if you know the droid data set, a lot of these tasks only have 1 repeated demonstrations. But for us, for every task, we have over 100 repeated demonstrations, so that even if you train just a low-level policy, you're still able to get it working. And however, in compared to other large-scale data sets that's collected, we are still far away from them. So for example, Pi, they have over 1.2 million episodes, robot episodes, whereas for us, even combining the mid-training data from MolmoAct data set is equivalent to 200K robot data sets. So how are we going to bridge that gap? So it comes back to the point of reasoning. So we know that in LLMs, people utilize intermediate chain of thoughts to do reasoning. But if you try to use that same form of reasoning concept in robotics, it might not work because reasoning in language is ambiguous to describe motions in space. So with that, we try to curate an action chain of thought data set that can be grounded. So the first thing we do is we take those robot trajectories. We have Momo to try to predict, like the points on the gripper. And if you stitch the points together, you can get a visual sketch of a plan that the robot wants to take in the next time step. And you're able to generate these sequential plans through every time step. And that sort of gives us the idea of, what's the planning context of robots in that case. And then furthermore, we want to make sure that we are not just doing reasoning on 2D pixels because that's much harder. We want to be able to move that into 3D or at least have some kind of implicit 3D. So with that, we train MolmoAct to actually incorporate perception token. That means we train with a bunch of robot data, leveraging the same kind of adaptation formula as this paper perception token, where we train a VQVAE that's able to sort of generate this latent codebook, which represents the perception tokens. And every robot data we will first pass through depth anything to generate the metric, the relative depth. And then with this perception token, now we can annotate ground truth annotations of each image corresponding to these perception tokens that they have. And with that, we are able to sort of put together this action reasoning data set. Basically, you have the observation of the robot. You have a question of what you want the robot to do. And the answer that's generated, or the answer pad that's generated, will be first predicting the depth token, followed by the trajectory tokens, followed by the action tokens that's necessary to do the task. And we also ensure that Momo is able to retain Momo's visual reasoning capability. So we use the same data mix that contains image caption, general knowledge VQA data set, and even pointing data set from Momo itself. And this is just a breakdown of Momo as pre-training data mix. We also included auxiliary depth token and line token so that it's able to actually learn better. And above that, we actually included this thing called a trajectory condition data set, which is basically given the image and given the sketch. Now the robot tries to predict the action. So we hope that by using this, we are able to steer the policy. So for training and inference of MolmoAct, so similar to VLA style training, we start off with a VLM. So for our case, we use Momo as the VLM as initialization. And then we train Momo in this 3-stage training: pre-training, mid-training, and post-training. And MolmoAct is able to do 2-stage inference, which is either to inference through reasoning in space or to do steerability. And for the training case, for pre-training, we use VQVAE together with the 19,000 robot data. The first stage of training tries to learn word knowledge and action understanding. And with that, we evaluated on simpler, which is a simulation data set that matches the distribution of what the pre-training data set compass. And we show that MolmoAct is actually able to perform in a SOTA performance as compared to many of these frontier labs vision language action models. And for the mid training, we basically incorporated this 10K robot episode, which is high quality. And MolmoAct basically learns actions from these specific settings with this high quality data set to do better alignment. And we show that, from our experiments in the real world, that if you use MolmoAct data set in this mid training process, you're expected to get a 5 to 10% performance gain in any of the post training tasks that you are using it for. And for the post-training, we actually train on specific downstream tasks. So that requires us to collect data for doing fine-tuning. We use LoRa for fine-tuning, and we're able to also deploy it for downstream tasks using action chunking. And we show that MolmoAct is really good at adapting for downstream tasks through both real-world experiments across different embodiment, and also in simulation through the Libra benchmark, showing that for at least autoregressive model, we are actually in the state of the art. And this is what one of the inference pipeline looks like, which is that MolmoAct is able to do reasoning in space, as I mentioned, trying to predict the perception token, visual reasoning token, and then the action. And also another thing is that MolmoAct is able to be steered. So because MolmoAct is predicting, the visual reasoning trace every time step, you can visualize out its plan or its intention. I'll put it in that way. And if you look at this diagram on the bottom, you can see the yellow line is basically what MolmoAct's prediction of the line, and it follows its intention as it moves towards the target object. And the task is to put the toy on the coaster. And the last frame, it decided to go for the coaster that's at the bottom. And then we come in, we draw a line ourselves, and we try to steer the policy towards, whichever direction we want it to go. And this is very important because language is ambiguous. So in our experiment, it shows that if you use language as a form of medium to try to steer your policy, it's not going to work as well as compared to using visual trace. And that's something that we've seen consistently in MolmoAct. And the broader impact of MolmoAct, since MolmoAct is only out for 2 weeks, we have over 20,000 downloads on our data set, and people already start building on top of it. And we are also able to see a huge amount of downloads in the checkpoints, and people are already deploying MolmoAct zero shot in the real world for different contexts. So that's sort of summarize the first part, which is spatial reasoning. I think the idea is that through this work, we try to propose a language condition pointing for spatial affordance prediction that could yield powerful intermediate representation, and also going one step beyond, to sort of define this chain of thought process that sort of supports reasoning in space, allowing MolmoAct to sort of surpass baseline methods with much less data. And I'll talk about the next component, which is on episodic reasoning. So for this, I'll introduce SEM2Act, integrating vision foundation model with a memory architecture. So to give a bit of context, most of modern days robot learning policy focus on the idea of imitation learning, which means that you're trying to maximize the likelihood of a policy to output its action condition on the observation and also the task conditioner. And most of the time, this observation could be an RGB camera, point cloud voxer, perceptions. And for the the conditioner itself, it could be natural language. It could also be image goal condition, or it could be points condition. And all this taken together with the robot action, and the output of that is to try to predict robot control, which could be a 7-DOF position. And most of these imitation learning policies are memoryless because, first of all, many of these benchmarks doesn't even require memory. And secondly, because these policies make the natural Markovian assumption, which is that the current, the future actions is determined based on the current state that it's in. And that's not really true because memory is crucial for manipulation. And I think this is not really soft and in that case. So with that, inspired by SEM2, we try to build a memory-centric robotic policy. We do this in a 2-stage approach. We first try to build a general-purpose manipulation policy, multitask manipulation policy, and then building on top of that, we actually incorporate the memory architecture from SEM2 to build SEM2Act Plus, which is for memory-specific tasks. So I'll talk a bit about the first one, which is the first stage to try to build this general-purpose manipulation policy. So we see that actually SAM2's image encoder is really good for generating object-oriented visual representation. In fact, it surpasses many of these other image encoder that's used for robotic manipulation, including Clip Dino R3M. And the way we sort of build this general manipulation policy is that we are taking a 3D observation in point cloud, we re-render it into orthogonal view, and then we'll pass that into SAM2's image encoder that's pre-trained to generate image embeddings, feed that into a multi-view transformer, and what it does is that it tries to predict a single embedding, and if you take the embedding, you do a convex subsample, you will be able to generate these action heat maps that covers different viewpoints, and on each of the action heat map, there will be a point that sort of represents the next action point that the robot should take. And because you have all these camera parameters, you can reconstruct that back into 3D, figure out a 3D point, and then you do a zooming on that, and then you do the same process one more time to predict the actual point that the robot should move to, and having a motion planner to actually move the robot towards that point. So the points that we sort of innovate on this architecture is that, first of all, we use the SAM2 image encoder to generate better visual representation that passes into the multi-view transformer. And secondly, because it's SAM2 image encoder, it has this advantage of generating multi-layer resolution embeddings. So we are able to actually, instead of what previous method does, which is a one-time convex subsample, we are able to do this multi-resolution upsample, which means that at every time step of the convex subsampling, we are actually concatenating the resolution embedding so that in the high-level intuition is that we are making the model see clearer and clearer without any loose information. And that pays off because we see that SAM2 is actually able to perform really well in terms of general multitask manipulation, over 18 hour bench tasks, which is simulation tasks. And because of this multi-resolution upsampling, we're able to see that SAM2 is able to actually work even better for like high precision tasks as compared to some of these baseline methods. So one example would be this. SAM2 compared to RVT2, which is a strong baseline, you can see that SAM2 is able to predict all these like next action point much better and more precisely than RVT. And this is the same example with the real world scenario where we try to train the policy to be able to turn on the lamp. You can see that RVT2 missed the lamp by slightly. And beyond that, with the SAM2 image encoder, we are able to see a huge bump in generalization. So this work Colosseum measures, systematically measures generalization in IO bench. And we see that with SAM2X, we're able to get the least degradation in terms of performance when we try to systematically evaluate it during test time by changing the environment texture, lighting, even table texture, adding distractor or background texture. And this is one example where now if you, the same policy, if you introduce distractor, you'll see that actually the baseline actually went for the distractor instead of the actual target. So that sort of gives us a really strong general purpose manipulation policy. And then with that, we build on top of it to adapt a memory architecture that is inspired by SAM2 to learn to remember past action. And the way we sort of do it is that we freeze the LoRa, the SAM2 image encoder and the multi-view transformer, which give good action prediction. But we incorporated the memory mechanism in the form of having a memory encoder, memory banker, and memory attention, connecting that to the multi-resolution upsampling process in a way that now after what comes out from the multi-view transformer will try to attend with past observations that's being encoded using a memory encoder and stored in the memory bank. So now that makes the action prediction more memory-centric. Obviously, to evaluate that, we need to have empirical experiments. So we want to sort of disambiguate the fact that the policy fails because of long horizon and not because of memory. So we design short horizon tasks that intentionally evaluate the memory. So for example, in this case, to reopen the drawer, there's only 3 steps. One of the drawer will always be open. The robot learns to close the drawer, press the button, which is to break off the Markovian assumption, and then figure out which drawer to reopen. And because the data is generated in a way that all 3 drawers will take turns to open, so you can guess that the baseline will achieve a success rate around 33% if it, at the very last step, is not able to make the right decision. And that's the case. So for example, a task like putting the block, we are able to sort of move the block to the center, press the button to break the Markovian assumption, and then figure out what is the original position of the block, whereas the baseline methods will basically make a random guess that it will be one of these 4 patches. And the same example goes in the real world, whereby the model is trying to press a button twice based on the location of the blue block previously. And once it reaches back its original state, it sort of breaks the assumption and then tries to figure out which one it actually pressed. So the baseline method will go for the other button instead. And the impact of episodic reasoning for robotic manipulation policies are really impactful. Not only because of that, we are able to achieve state-of-the-art performance in our bench and was featured in the AI Index report last year, but we are seeing more interest towards like memory-based vision language policies, or even benchmarks that comes out that focus on evaluating memory for this kind of action models. And that sort of covers the second part of episodic reasoning, which now we are looking at incorporating a memory architecture into policy to induce implicit episodic reasoning and improve action prediction. And memory is really crucial for most of the real-world tasks, and most of the current existing methods are sort of missing in. And for the last part, I'll talk about semantic reasoning through this word AHA, which is a vision language model for detecting and reasoning over failures in robotic manipulation. So we know that many modern robotic systems leverage language model, vision language model in any aspects to sort of automate their process. So one example will be Eureka. So how Eureka works is that it has a language model to generate multiple dense reward functions, and then you train RL policy using those dense reward functions, get the best reward, and reiterate that reward function using a language model to generate the next best one. And you're doing this in terms of a search. But the problem is that if you know exactly what went wrong in the first time step, you're able to sort of narrow down that search very fast. And the way to figure out what went wrong is to be able to detect when the action fails, and also to provide a natural language reasoning on why it fails. So conventionally in robotics, people detect failure through binary detection. So they could either train a classifier, or these days people just use off-the-shelf VLMs to try to detect failure. But in my early slides, we show that it doesn't really work, even for frontier models. So the one that we sort of try to achieve is that we want to come out with a VLM that's able not only to detect failure in terms of binary success, but also to be able to generate a reason to explain why something failed and provide exactly at which time step did it fail. So in order to train such a VLM, we need failure data. So the way we sort of do it is that we turn to simulation for the solution. We first create a taxonomy of potential failures that you expect to see in robotics. This can range from incomplete grasp to inadequate grasp retention to even wrong action sequence or to like wrong object selection. And then with that, we take an existing data set that generates successful trajectories. We systematically perturbate through all the different trajectories and inject the common failure mode that we have defined. And then we re-render that to generate failure trajectory. And because you have a success condition at the end to detect, we only append in those that fails. And by doing so, we are able to generate this this QA pairs of these trajectories to explain why it fails and knowing exactly at which frame it fails. And with that, we did the same kind of full fine-tuning on Lava 1.5. And obviously, we also added like co-training data set. We also added co-training data set beyond the AHA data set, which is all failure trajectories. We had the VQA and also like localization data set. And we show that we are able to actually, give a sequence of observations. The model is now able to, explain and predict whether have the task described succeeded or failed. And if it fails, what is the reason behind it? So to evaluate that in a more empirical way, we look at 3 data sets for failure detection and reasoning. So for us, we actually have a held out data set of 20 tasks that was never seen during training. To evaluate generalization across tasks, we use another data set called RobotFail, which is from Stanford. They manually collected robot trajectories in the real world of a robot doing tasks and also failing at certain sequence. And we also use the same way of generating failure data to try on a totally different domain in many scale. And we evaluate that across many different VLMs, both open source and closed source, and we realized that AHA is able to outperform many of these models, not just in one metrics, but in 4 different metrics to measure from binary success to semantic similarity in meanings to even judging, having a language model to judge the context of the 2 outputs. So with that, what can we really do with AHA 13 billion, which is a VLM that is able to reason about failure, and how can we sort of use that for robotics? So I guess the idea is that now you can sort of redesign dense reward function in the Eureka setting, whereby now Eureka is able to generate the first iterative dense reward function. You train a policy and you roll out that policy. AHA looks at that policy and give a feedback of what it thinks went wrong, and you can use that to sort of generate a new dense reward function that included a penalty along the misalignment of the z direction. And this is also really good for like training reward models that's potentially useful for robotics. And furthermore, we can actually use that for replanning in a task and motion planning context, where a temp system could generate a plan. We roll out that plan and we realize that it doesn't work. AHA comes in and generates a failure, and we use language model to correct that plan that was generated. Now we're able to have successful behavior. And we could also use that for step-by-step open vocabulary data generation to provide binary success feedback. In this word, manipulate anything. And we show that, by using AHA, we outperform frontier models like GPT-4o in terms of detecting and reasoning about failures. And the impact of failure reasoning for robotics has really been, obvious, because previously people are not really thinking about the need to actually come up with implicit reasoning in the form of text to explain why something went wrong. But with the review of AHA, many people are sort of inspired by that line of thoughts, and there's small paper that's focus on robot failure detection for safety alternatives, or even to have this kind of replanning with like vision feedbacks through language instruction following, and we see a much more interest towards that direction. So with that, so summarize the part 3, which is focused on semantic reasoning, the idea whereby we're able to show that direct sim to real transfer is feasible at semantic level, for example, at least for reasoning over failures, failure trajectory in robotics. And also we also show that reasoning about failure in robotic manipulation offers a better initialization and more grounding for robotic systems that leverages LMs and VLMs in that pipeline. So with that, come to the end of my talk. Let's thank my collaborators, and I'm also open up to any questions. Yeah. Thank you.
Yeah, thank you so much for coming today. This was super interesting. I think a lot of the work you guys are doing is research directions that make a lot of intuitive sense, that when you first hear it, it seems so simple, like, yes, of course we should do that, which I think is a sign of good research, that it seems simple, but it's really, it's a really complex idea. So thank you so much. One question I had, for the co-training set for failure data, were you getting reasoning labels for those?
So for this one, yeah. So for this one, we generated our own failure trajectory labels, and the way we do it is in a clever way, in a way that it's really easy to get robot to fail in the real world, but you're not able to get ground truth labels. So the way we sort of do it is that we look into having trajectories that succeeded in simulation. So these are, for example, pouring milk into cup. That task succeeds. And because we predefine all these different failure modes, we can systematically inject these failure points in simulation to create that failure, occurrence. And because it's in simulation, we can measure whether each trajectory has succeeded. And if it does succeed, then we don't really want that trajectory. And if it fails, and that will be the trajectory with that ground truth label to explain why it fails. So these are all generated systematically in simulation, because that you can provide the ground truth label in a much easier way. Yeah.
Gotcha. You mentioned there's a co-training step as well, where the data mix is.
Yeah.
Are there labels for the real world data?
So the real world data are just regular data. They're just QA data and like localization data. So most of the failure trajectory, or I would say 100% of the failure trajectory, comes from simulation, which that's pretty cool, because we see that there is a transfer from sim to real, at least in terms of semantic reasoning of failure.
Yeah. It's really interesting, the like representation. You call it representation learning if you want, but the representations transferring is really it's really cool to see that in sim. I'm doing some work right now
cool.
that we're hoping for the same thing. So
and I think even coming back to the RoboPoint example, you realize that the way we generate this kind of affordance prediction data is also purely from simulation. So I think here, so for this one, we are also generating purely from simulation. You can see that this is actually a simulation environment. We generate all these object assets, and then we know the ground truth position of the objects, and then we can alter that simulation in a way that cleverly to generate these kind of free annotation points. Yeah. So these are, and it transfers really well because it's the data only have kitchens, but we can generalize to roads. So that's pretty, yeah.
Really cool. Yeah, thanks for answering that question. I think there's a bunch of other questions maybe from hands raised. So.
Oh, yeah. That's a person. So I saw someone raise the hand.
Yeah, Jiafei.
That was a great talk, Jiafei. So I have a question about the episodic memory part.
Okay.
So you talked a lot about how it is useful in manipulation tasks. So I was wondering if you could generalize the same to navigation problems, and whether the same model would be able to say help a car navigate through a road. Because say you're using it in autonomous driving and you want to take a reverse. I feel that having a memory of what was the previous action of the car could be super useful.
Yeah, for sure. So I think in this case, we are trying to solve short sequence spatial memory in a way that is the robot performing action and immediately it does something else and it tries to perform and tries to recall where the previous action was. I think in the car context, I think it makes sense for longer context to be represented, longer context memory to be represented in a different way. But obviously, you also want to have some form of what we show in Semantic to sort of learn short snippets of actions that the autonomous car takes to remember what's the action that it has taken. And also a lot of times these days they do end-to-end network training for autonomous driving. So how are we able to implicitly incorporate memory into this kind of policy learning? You could draw inspiration from Semantic. Yeah.
Yeah. Thank you.
No problem. Yeah.
Nahi?
Hey, hi, Jiafei. Nice to see you again. Yeah. So yeah, I was wondering. If you look at some of the work from physical intelligence, at least the one that are open source, they're really focused on action tokenization and the techniques they can do around that. I see that your line of work is really very, very different bucket from that.
Yeah.
So I was wondering, what is maybe your thought on the problems that you are trying to solve on episodic reasoning or spatial reasoning? Can those be done also with their approach? How do you think?
So I think there should be a marry in terms of their approach versus our approach, in a sense whereby we are focused a lot in terms of the reasoning aspect, and then the thing that's sort of missing out is the low level dexterous policy learning. But also there is a trade-off to what they are sort of doing, right? Because they're just heavily relying on scaling data. But as I mentioned at the very start of this talk, it's really hard to actually scale data in the same level as how LLMs has been doing to sort of train some of these large language models. And I think that when data is not enough, at least in MolmoAct example, we show that reasoning could actually empower the model to perform comparable to even Pi. So I think in that context, then maybe we are able to provide a different lens in terms of how we actually look at this. And at least in my context, we feel that able to get good representation that can do this kind of intermediate reasoning will actually help you to learn action better. Learning in the way of not just overfitting to the action, but to be able to interpolate and reason about or generalize to a new kind of observation. So I think that leads to better performance. So I think yes, but then obviously there is also another component which is to be able to learn really dexterous manipulation, and that still requires data. Yeah.
Thank you for sharing your perspective.
No problem. Yeah.
I wonder if part of that too is also Pi is a startup, and as a startup, you want, what is your moat? Data.
Yeah.
Research is great, but everyone's going to keep doing research, and you can piggyback off of them. I need to collect my moat.
Yeah, for sure. I think I totally agree. I think if you look at it, Pi is really good because they actually released they released that checkpoint, But actually, the thing that's valuable here is the data. Yeah. Yeah.
Sergio, looks like you're next.
Hi, Jiafei. Thank
Hi.
you very much for the presentation. Very interesting. I have a question.
Yeah.
What do you think is the next step in the research process for spatial reasoning and robotic models?
I see. Yeah, so I think the next part of what I think is the mode is to be able to also, of course, when we propose MolmoAct, we are proposing this idea of an action reasoning model. But obviously, the way we sort of represent reasoning is through this like grounded chain of thought process. But reasoning could exist in many different ways, right? So I mean, or different representation. So these are things that we haven't sort of discovered. So I think my really interest or research direction moving forward is this notion of looking at the the dark matter of robotics foundation model, because like the observable matter, which is what we see in the universe, these are things that you can observe through what we see and the actual things that are in front of us, and these are in the robotics context, those are like visible actions. But there's a huge amount of unobservable things that you have to be able to reason across that you can't get from just visible actions. So for example, how do you incorporate tactile? How do you incorporate even like sound? And also, having this kind of multimodal inputs to sort of train your policy to be able to, learn better action. Because humans uses multiple sensory. We are not just using perception from the sense of like, what we see, but in terms of what we touch and what we feel. How do you sort of incorporate that into building this kind of action reasoning model? I think that's something that I think is my personal interest moving forward.
Okay, that sounds good. Thank you.
Thank you. Yeah. Feel free to any more questions. Just
Hi, Jiafei. This is Adarsh. Thanks for this talk. First of all, my question is more of a generalist, totally new to the space. I just wanted to know your opinions on. So recently, I've been in this NVIDIA GTC conference where their emphasis more on the digital twins, basically the OpenUSD 3D simulations for where the robotic data is not openly available. So what's your take on it? So I mean, some part of your talk did mention there's a limited data for actions, right? So
yeah.
Why not the research advancing in using that stimulations to create synthetic data, perform actions? So what's the real life implication? I just wanted to know your perspective on it.
I think that's a good question. So I think like simulation data or synthetic data are really useful. Right. And as I mentioned, you can't scale robot data in the real world to the same level as how people train language model. So simulation is definitely a way forward. But right now there is still a domain gap between simulation and the real world. That means you don't expect it to work right off the shelf because there's a either visual domain gap or physical domain gap in terms of the physics interactions. So that's something that will need to be bridged over time. But at least in my work that I presented just now, we also use simulation to generate large scale data to train these like robot specific VLMs. And for those data, we generate in a very different representation. We don't generate action. We don't generate direct action. We generate, for example, we generate failure reasoning, explanation. And for RoboPoint, we generate this like 2D affordance, spatial affordance prediction points. So these are things that could transfer sim to real much easier. Obviously, locomotion is also another example that could transfer sim to real pretty easier because they are state-based. They don't require vision. So I think there is going to be this gap between simulation and the real world. But over time, this gap might be bridged, and simulation will be the engine to sort of generate more of this data. But right now, we feel that, at least for my approach of using simulation, is to generate this kind of high-level data that could be useful for robotics and transfer that into the real world. Yeah, because that gap will be shorter. Yeah.
Sure. Thank you.
No problem. Yeah.
Probably going to be the last one. Thank you for the lecture. It's very enlightening. It's very nice. Especially for me because like bulk of my work at the moment at NYU is the actually reasoning in multimodal and embodied models. But most of mine actually revolves around like interpretability angle of it, which is something that's definitely not been explored a lot. I have like a two-part question. So first part of it is kind of like on your personal level after like doing this like research and different kinds of reasoning. Do you think the problem of like failures over like, let's say like long horizon tasks, some specific tasks have to do like more with the model lacking some kind of like semantic understanding, so like some multimodal lack of it, or is it like more of a manipulation kind of side and failure that's coming in, so the model doesn't know like the physical grounding really well? Like which one you would like kind of rate in terms of like ratio of what contributes to the failure?
Yeah, so I think it's a lot of times is because like these models, it's just hard to actually obtain data that covers this spectrum. And how do you actually, efficiently get such data, as we mentioned just now previously, which is that, for example, a simple thing as, robot failing. Like it's easy to, have failure observed in the real world in a robotic system. But how do you generate that label? How do you do it in a clever way to generate, ground truth annotations that is able to use to train some of this model and incorporate that capability? I guess like the way people train such multimodal language models has already sort of saturated. It's more of like how can people come up with more, useful data sets or more creative ways of obtaining data that previously you can't extract, and try to learn that capability from this data distribution, and showing that learning on this is able to generalize to a broad range of tasks. I think that's basically like what everyone is focusing on. I think that in that sense, I think it's not that the language model, VLMs these days cannot do that, but it's just that they don't have the capability sort of taught into it. Yeah.
Again, I like that.
Sorry.
Second one,
Hello.
and that for language models, hopefully you guys can hear me. I hope it's okay.
Yeah, it's okay.
You cut out at the beginning there.
Happening, honestly, it's not the first time. Like it's the second time I hear this today, by the way. Yeah, the question I had is like, I remember reading earlier papers in sort of like the attempts to integrate like VLMs into like self-driving, which, like at least for me, I find it kind of like questionable because of the latency, right? Chain of thought and all that stuff introduces kind of like the time, like the test time required, like to like kind of think through the steps, et cetera, et cetera. But then like, does it really work for many scenarios in robotics where like latency, like supposed to be short, like the speed like is required, like you have to think fast. Because like, especially for like, let's say intermediate steps, like maybe at the start you could like figure this out, but then like, I'm still wondering, like, what do you think of that?
Yeah, so
in terms of like this trade-off?
I think that's a good question, because like in robotics, more than any other task, latency matters, especially in autonomous driving or even in manipulation. So the way we sort of look at this is that, the way we can potentially do this is to not do reason at every time step, but having some form of formulation to do iterative reasoning, or like, figure out when to reason. So I think that could be a way to sort of address this problem. Yeah. Okay. Yeah. Thanks, everyone.
Yeah. Jiafei, thank you so much for coming and presenting. This was this was so fun. This is like the best way to break up the middle of the week. So thank you, for doing this.
Yep. Okay. Yeah. I knew like this is one of the best presentations we had at multimodal group. So thank you for that.
No worries.
And also like one of the questions like audience was asking about like how they can get the access to the presentation.
I can share it.
Yeah.
I can share it with you guys. Yeah.
Okay, then yeah, I'll just talk with you after the call so that you can share with me. I can share with the whole rest of the Discord group.
Yeah, sounds good. Yeah, sounds good. Thanks once again for inviting me. And see you guys in the future.
Yep. Thanks again.